All right, so let's talk about questions 6 and 7. Questions 6 and 7 are asking you about the transformation of a function graph. So I've listed the rules here, and I thought it would just be easiest to show you what they mean in terms of a graph. So the first thing that I'm going to do is I'm just going to start with a quadratic function, and I'm going to start with the parent function y equals x squared. So if you remember, you can make a table of values, but we talked about the rules, right? We're really focused in math 2 on kind of knowing the rules or recognizing the pattern. So if I take -2 and I square the quantity, I get +4. -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So I'm just going to plot this parent function. I want to graph it so you can see when x is 2, y is 4. Let's see, 3 squared is 9. I can actually fit that on my graph. And remember that we have this axis of symmetry, so everything on the opposite side is really a reflection. So this is the parent function of a quadratic. So if I were to add 3, I want you to think about where the vertex is of a parent function. The vertex is at the ordered pair 0, 0. If I were to take x squared and I were to add 3, we learned about vertex form. We're not adding anything to the square function. We're adding something on the outside. So if I were to take x squared and add 3, well, -2 squared is 4 plus 3 is 7. So when I am at -2, I'm actually going to go up to 7. So the shift was a movement of 3, because typically when x is -2 and I square that, thinking of the parent function, I move up 4, but when I add 3 to it, I'm going to move up to the 7, which means it's a shift of 3, and it's a vertical shift. So, and I know that's a lot. I'm just trying to show you visually why this works. So when I think about a number on the outside of the function, so, and what I mean by that is, like, if I have x plus 2, the quantity squared, plus 5. This is the number that's outside of the square function. So the number outside is representing a vertical shift. So this +3 means that my graph shifts up vertically 3 units. So if I have a negative outside of the function, this says the function with a minus something, it's going to shift down vertically 4 units. And I want to show you on the graph what that looks like. So if I were to take x squared and I were to put a -4 out here, so x squared minus 4. So if I let x equal 0, 0 squared is 0, minus 4 is -4. 1 squared is 1, minus 4 is -3. -1 squared is 1, minus 4 is -3. So what I want you to see is that I'm actually taking this graph and I'm shifting every point down 4 units. That's what's happening. So a function with an addition or subtraction outside, see how it says the function and then an addition or subtraction outside, that's going to be a vertical shift. If it's positive, it's moving up. If it's negative, it's moving down. Okay, so now let's look at our next example. So I'm going to try and erase all the stuff that I drew around our parent function. So our next example has f times, or f of x minus 1. So this subtraction of 1 is taking place inside of the function. So that really looks like y equals x minus 1, the quantity squared, in terms of a quadratic. I'm trying to show you guys this in terms of a quadratic or a parabola because you should be familiar with those. Well, I'm going to make my table of values again because I think that it's important for you to see what's happening. And I'm going to start with the parent function, and then I'm going to throw in this x minus 1, the quantity squared, and we're going to see what happens. So parent function, negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, positive 1 squared is 1, positive 2 squared is 4. But now I'm letting x equal negative 2, and I'm plugging it into this function so you can see what happens. So negative 2 minus 1, well, that's negative 3. And when I take negative 3 and I square it, I get a negative 3 squared is 9. When x is negative 1, negative 1 minus 1 is negative 2, squared is positive 4. When x is 0, 0 minus 1, running out of line here, 0 minus 1, the quantity squared, is 1. when x is 1, 1 minus 1, well, 1 minus 1 is 0, and 0 squared is just 0. And when I let x equal 2, 2 minus 1 is 1, and 1 squared is 1. So when I graph this x minus 1, the quantity squared, when x is, ding, ding, dong it, when x is negative 2, I'm at positive 9. And when x is negative 1, I'm at positive 4. And when x is 0, I'm at positive 1. And when x is 1, I'm at 0. And when x is 2, I'm at 1. And if x were 3, if I had that value in here, 3 minus 1, the quantity squared, is 4. So hopefully you can see that I took my parabola, my y equals x squared, and I moved it to the right. So when you have a subtraction inside the function, it moves to the right. It's counterintuitive. I know it doesn't sound like it should move to the right. You would think it would move to the left, but it doesn't. So when you have a subtraction taking place inside of the function, it's called a horizontal translation. So you're moving it horizontally to the right. And this is moving 1 unit. So when I'm going to jump down to this one down here. So f of x plus 2. So now I have an addition taking place inside of the function. And so I'm going to, again, show you what it looks like visually. So I'm going to use my parent function. But now I'm going to write, my pen is dying. So now I'm going to write x plus 2, the quantity squared, and I want you to see what happens. So we're going to take x plus 2, and we're going to square that. So negative 2 plus 2, well, that's 0. And when I square it, I get a 0. When x is negative 1 plus 2, well, that's 1. And 1 squared is 1. When x is 0, 0 plus 2 is 2. And 2 squared is 4. When x is 1, 1 plus 2 is 3. And 3 squared is 9. When x is 2, 2 plus 2, well, that's 4. And 4 squared is 16. So I'm going to graph this in red so you can see it. So x plus 2, when x is negative 2, I'm at 0. When x is negative 1, I'm at 1. When x is when x is 0, I'm at positive 4. When x is 1, I'm at positive 9. And you probably need to see what happens when x is negative 3. So negative 3 plus 2, well, that's negative 1 squared, but negative 1 times negative 1 is a positive 1. So this is my graph. Maybe try and highlight it in yellow so you can see it. So I've taken the parent function, which was at 0, 0, and I moved the vertice 2 units to the left. I moved the vertice 2 units to the left. So when you have a function with addition inside of the function, just like we had that x plus 2, the quantity squared, it's still a horizontal movement. Horizontal moves you to the left and to the right. So this horizontal translation is going to move you left 2 units. Left 2 units. All right. So the last three that we need to talk about have negatives in them or a stretch. So let's look at this. So example C, y equals negative f of x. So that just means you're going to take the parent function y equals x squared, and you're going to put a negative out in front of it. So let's take a look and see what that looks like. So I'm going to take my parent function y equals x squared. So parent function y equals x squared, and I'm going to rewrite it so it has a negative out front. So you're just going to take all of your outputs, and you're going to make them the opposite. So the opposite of when x is negative 2, the opposite of a positive 4 is a negative 4. The opposite of positive 4 is a negative 4. The opposite of a positive 1, negative 1. 0 doesn't have an opposite, but all of these are going to get the opposite sign. So hopefully you see what happens is you just take this parent function and you're flipping it. It's called reflecting. You're flipping it over the x-axis. You are reflecting this over the x-axis. So all you do is flip it. So for example C, what's happening? Describe the change in the graph. This is a reflection over the x-axis. This is a reflection over the x-axis. All right, so I'm going to erase all of this stuff that I've added here just so we can kind of still look at the graph and look at the picture. And I'm just going to graph the parent function again. So parent function, y equals x squared. So remember about the axis of symmetry. You learned that in Math 1 and Math 2. Remember, it's that line of reflection. So I'm going to start with y equals x squared. That's what I have graphed there. That's what this table represents. And now I'm going to put a 2 out in front of it. So y equals 2 times the quantity x squared. Well, all that means is I'm going to take all of my outputs and multiply them by 2. So 4 times 2 is 8. 1 times 2 is 2. 0 times 2 is still 0. 1 times 2 is 2. 4 times 2 is 8. My pen is not working. And if I had a 9 here, 3 squared is 9. 9 times 2 is 18, but we're not going to need to go up that far. And so I'm going to plot this in green. I'm going to put this on the graph in green, and hopefully you can see what happens. So when x is negative 2, I'm actually going up 8, all the way up to the 8. When x is negative 1, I'm going up to positive 2. 0, 0 stays where it is. When x is positive 1, I go up to 2. When x is positive 2, I go up to 8. So you can see that your parabola was stretched. It was stretched, and this is called a vertical stretch. And the number 2 out front says that it's a vertical stretch with a factor of 2. So it was stretched by a factor of 2, meaning I took every output from the parent function and I multiplied them by 2. I took every number here, multiplied it by 2. Okay. The last one that we want to talk about is this right here. And this is the inverse function. This is the inverse function. And the inverse function reflects over the line y equals x. The inverse function reflects over the line y equals x. So I am going to draw the parent function And I am going to show you what that looks like when you reflect it. So the line y equals x is just that. It's just a line with a slope of 1 going through the origin. That's the line y equals x. So when I reflect this, a couple of things. I notice that 0, 0 is on the line, so it doesn't move, and so is the point 1, 1. But when I try to calculate the inverse function, and remember, we're talking about the function y equals x squared. Well, when you want to figure out the inverse of a function, you actually replace the x and the y, and you solve for y again. So I want to show you what that looks like right here. So I'm going to find the inverse. I'm going to find the inverse of this function. So the graph is y equals x squared, and I need to find the inverse of it. So I'm going to take the function y equals x squared, and I replace my x and my y. I change spots. And then I solve for y. Okay, so the only way that I can solve for y is to take the square root of it. The only way I can get y squared by itself is to take the square root. But remember, if you square root one side, you have to square root the other. So the square root of x equals y, meaning y is the square root of x. It's the square root function. Okay, so let's think about graphing that. So if I let x equal 1, the square root of 1 is 1. I'm going to make a little table of values for you. If x is 0, the square root of 0 is 0. If x is 1, the square root of 1 is 1. If x is 4, the square root of 4 is 2. If x is 9, the square root of 9 is 3. Notice that I'm only picking perfect squares. So when x is 4, y is 2. When x is 9, y is 3. Okay. Well, notice that I can think about when you physically draw a square root function, you have to remember that it could be a positive or a negative, right? So when I say, what is the square root of 4? The square root of 4 is 2, but it also could be negative 2, right? Because negative 2 times negative 2 equals 4. So when you think about these answers here, you could also have when x is 1, y is negative 1. When x is 4, the square root of 4 could be a positive or a negative, right? The plus or the minus root. When x is 9, I have the positive or the negative. So when x is 1, I could have an output of negative 1, 4, negative 2, and 9, negative 3. So all I've done is I've taken this parabola and I've actually rotated it 90 degrees clockwise. But really, I mean, that's what it looks like. But honestly, it's a reflection over the line y equals x. It's called the inverse function. I know this is a lot, but we're going to do that. We have some questions later on. I think 9 through 11 are about inverses. Okay. So now I'm going to do number 7. I've probably graphed you to death, but this is really important. These rules are really helpful. So use those. And so we're going to start with, you'll notice for number 7, it's just A through F, I think. All of these are a transformation of the absolute value function. So the function y equals the absolute value of x. This is the parent of the absolute value functions. Just like we have y equals x squared as the parent of all quadratics. So it just means that all absolute value functions are derived from this. So I'm going to make a table of values just to get you started. So if I let x equal negative 3, the absolute value of negative 3 is 3. If I let x equal negative 2, the absolute value of negative 2 is 2. If I let x equal negative 1, the absolute value of negative 1 is 1. If I let x equal 0, the absolute value of 0 is 0. If I let x equal positive 1, the absolute value of that is 1, positive 2, 2, positive 3, 3. So it really just looks like this. That is what the absolute value graph looks like. It makes a V. So here's your function, just like this, right? So think about all of the things. So let's talk about the domain. Domain, we can use any real number, right? So the domain is all the reals. The range is your y values. The range is your y values. So you notice that the smallest y value in my function is 0. So that means that y is going to be greater than or equal to 0. Now let's transform this. I'm taking the parent function, this plus 1 outside of the absolute value function. A plus 1 outside means that I'm going to move everything up 1 unit. And this 2 in front of the absolute function means I'm going to multiply by 2. So here's what we're going to do. The first thing that we're going to do is we're going to take all of our outputs right here. These are your outputs, and we're going to multiply them by 2. So when x is negative 3, I get a positive 3. But positive 3 times 2 is 6. When x is negative 2, I'm at positive 2, but positive 2 times 2 is 4. You see what I'm doing? Positive 1 times 2 is 2. 0 times 2 is still 0. 1 times 2 is 2. 2 times 2 is 4. And 3 times 2 is 6. And then I have to add 1 to that. Well, that's what's happening algebraically. But honestly, what you're really doing is you're moving it, you're taking the vertex up from 0, 0, you're moving it up 1. And then when x, your output, when x is 1, your output is now going to be 1 times 1, like the absolute value of 1 times 2 is 2. And then you add 1 to it. So it gives you 3. When x is, so I don't know if that's making sense or not. I'm adding 1 to all of these, right? So when x is 2, when x is 1, the output is 1 times 2. So now I have an output of 2 because this makes me multiply by 2, and then I add 1 to that. When x is 2, my output is 2, but 2 times 2 is 4, plus 1 is 5. When x is 3, my output is 3, but now I have to multiply that by 2. 3 times 2 is 6, plus 1 more is 7. And this is the absolute value function, and so it's really symmetrical, just like a parabola. So I can actually just go on the other side of the axis of symmetry, if you will, and just mark those. And that is what this looks like. So it has a vertical stretch and a vertical shift, vertical stretch of 2 and a vertical shift. The domain is still all real numbers, but the range is now positive 1 is your lowest y value. So y is greater than or equal to 1. Okay, so I'm going to talk you through these quickly because my computer is going to die and I need to go find my cord. So next one, this is going to reflect. It's going to reflect over the x-axis. This is going to move you to the right, and this is going to move you up 3. So you could take the point 0, 0, move it to the right 1, and then instead of moving it up 3, since you're reflecting over the x, it's going to move this way. So that's what's happening for here. We'll pause our video and we'll pick back up.